This slide is the first in electrochemistry series. The first set of slides covered two topics from Harris' textbook, chapter Fundamentals of Electrochemistry. First topic, Basic Concepts, and the third, Standard Potentials. I skipped the second topic, so only 1 and 3. You can read it yourself. Please read these two topics in your books. Pages are different in different editions. First, what metric units we are using in electrochemistry? In modern approach, in your older books you may have different table. There are numbers of values that are exact, will not change, and are the basis of new metric system. One of them is elementary charge, which is the charge of one electron. Unit of electric current, ampere, is the current of 1 coulomb per second with value of elementary charge fixed and the value of second is defined separately. Other units that we are using in electrochemistry are usual units of power, watt, which is joule. Joule is a unit of energy per second. Another is quantity of electricity, coulomb, which is current in amps multiplied by seconds. Next is voltage unit, volt, used for electric potential, potential difference, electromotive force. I think we'll never mention the electric resistance unit, ohm, but still it's important. Now, oxidation reduction reactions, or simply redox reactions, involves transfer of electrons from one species to another. The species is said to be oxidized when it loses electrons. It is reduced when it gains electrons. Oxidation agent, called an oxidant, takes electrons from one substance and becomes reduced. Reducing agent, also called reductant, gives electron to another substance and is oxidized in the process. In reaction between Fe3 plus and vanadium 2 plus ions, making Fe2 plus and vanadium 3 plus, Fe3 plus is the oxidizing agent because it takes electrons from V2 plus. Vanadium 2 plus is the reducing agent because it gives electron to Fe3 plus. Fe3 plus is reduced and vanadium 2 plus is oxidized as the reaction proceeds from left to right. You can find oxidation numbers and balanced redox equations in Appendix D. So oxidation is loss of electrons. Reduction is gain of electrons. Oxidizing agent takes electrons. Reducing agent gives electrons. There is a relationship between units used in chemistry and units that are used in electricity. In chemistry, we prefer to count everything in moles. So how much charge will be in 1 mole of electron? There is a simple relationship between them with conversion constant named Faraday constant after Michael Faraday. It's simply the coefficient that converts moles into coulombs. It's a relatively big number, 9.610 power 4. So, quick example how to relate coulombs to quantity of reaction. If 5.58 grams of Fe3 plus were reduced, how many coulombs of charge must have been transferred? First, the moles of iron reduced are, take this weight, divide by atomic weight of iron, and you'll find it's 0.1 mole of Fe3 plus. Each iron ion requires one electron in the reaction equation. Using Faraday constant, we find that 0.1 mole of electrons require 0.1 mole multiplied by Faraday constant, 9,000 coulombs. You can test yourself by doing very similar assignment for SN4 plus to SN2 plus. Keep in mind that there are two electrons in this reaction. Now, electric current is quantity of charge flowing each second through the circuit. The unit of current, of course, is ampere. 1 ampere presents flow of 1 coulomb of charge per second per point of circuit. Suppose that electrons are forced into platinum wire immersed in solution containing SN4 plus ions, which are reduced to SN2 plus at constant rate of 4.24 millimoles per hour. How much current passes through the solution? Now, there are two electrons that are required to reduce one SN4 plus ion. Electrons flow at rate 2 millimoles of electrons multiplied by 424 millimoles of tin per hour. Now, it's very inconvenient unit. We need to convert hours into seconds. There are 3600 seconds in an hour. So our result will be 2.310 to the negative 6 mole of electrons per second. To find current, we convert moles of electrons per second into coulombs per second. How we do that? Just multiplying by Faraday constant. And we're receiving 227 milliamps or 0.2 amp. Please look at, you see, we had very low number of moles, 210 to the negative 6, but current is very visible, 0.227. So large currents result in relatively small number of moles. Next, relationship between voltage, work, and free energy. There is general relationship between work, potential, and amount of charge from physics. Work equal to potential. In this case, we are using volts, and amount of charge, of course, in coulombs. Now, maximum work that 1 mole of specific reactant can do in chemical reaction is named delta G, the difference in free energy. This is from your thermodynamics chapter in your second semester general chemistry textbook. Therefore, a relationship between free energy difference and electric potential will be delta G equal to number of electrons multiplied by Faraday constant. So we are converting number in moles in units of electricity and multiply by potential, which of course is in volts. E potential is a maximum voltage that can be generated by a reaction if it's conducted slowly, reversibly at equilibrium at constant temperature and pressure. Sign of minus coming from agreement in which way the number will change. You can put plus here, but then your potential will have opposite sign. There is international agreement that we are putting minus in this equation.